Additional exercises. Question 25. An oil drop of 12 excess electron. 12 excess electron indicates the total charge in the oil drop Q is equal to Ne, that is equal to 12E. Is held stationary under a constant electric field 2.55 into 10 power 4 Newton per Coulomb in Millikan's oil drop experiment. So here we can have an oil drop carrying charge 12V, which is equal to Q, and M is the mass. So gravitational force is acting on the oil drop. We can take it as Fg, gravitational force acting downwards. Now assume that an electric field is acting, electric field E is acting downwards, and Q is negative because of excess electron. In such a situation, a negative charge experiences force opposite to electric field, that it is acting upward. Force due to electric field Fe is acting upward. And when these two forces Fg and Fe, when they are equal and opposite, then the drop remains stationary at the point. An upward electrostatic force is equal to downward gravitational force, and electrostatic force is QE is equal to gravitational force is mg. Now Q is equal to 12 electronic charge into E, electric field is given, and mass of the drop is volume into density. Volume is 4 by 3 pi r cube, density rho into g. Now you can cross multiply this equation, then take the cube root of the equation and find the value of r, the radius of the drop. Then next question 26. Which among the curves cannot possibly represent electrostatic field lines? Here you can see the first diagram. Electric field lines enter or emerge normally through a surface. Here in most of the lines are not having normal emergence, therefore this diagram is wrong. Now for B, here it is shown that the field lines are entering the positive charge, which is not possible. Field lines always originate from positive charge, therefore this diagram is wrong. Diagram C is correct. Diagram D is again wrong because field lines cannot intersect each other. Diagram E is also wrong because electric field lines cannot form closed loops. Now question 27. In certain region of space, electric field is along z-axis throughout. The magnitude of electric field is, however, not constant but increases uniformly along the positive z direction at the rate 10 power 5 Newton per Coulomb per meter. That is the rate of change of electric field along z-axis. d by dz is given as 10 power 5 Newton per Coulomb per meter. What is the force and torque experienced by a system having a total dipole moment 10 power 7. Dipole moment is given 10 power minus 7 kilometer in negative z direction. Dipole moment is acting along negative z direction. Now we have the formula F is equal to QE. Here the electric field varies with a rate dE by dz. So in this case, V is equal to Q into E, and the formula we can Q into D, we can take small variation of electric field, and this formula can be divided and multiplied by dz. So F is equal to dz into Q into dE by dz. dz is an arbitrary distance and q is the charge. So dz into q will give a dipole moment P into d by dz, which is given in the question. So substitute the values of P and d by dz. You will get the force acting on the system. Now the torque formula is torque tau is equal to P sin theta. Tau is equal to P sin theta. Here it is given the dipole moment and electric field. Electric field is along positive z direction, while dipole moment is along negative z direction. So angle is 180 degree, and sin 180 is 0. As sin 180 is 0, then the total torque acting on the system tau is equal to 0. So you will get a force and torque on the system. Now question 28, a conductor A with a cavity is given a charge Q. Show that the entire charge must appear on the outer surface of the conductor. So here, according to Gauss theorem, and in the case of the shell, we have seen electric field inside a cavity and a conductor is 0. So when you take at any point the electric field you will get 0 inside the conductor as well as inside the cavity. Now imagine a spherical Gaussian surface inside the conductor. Now electric field is 0. We have flux phi is equal to EDS. As electric field is 0, flux phi is equal to 0. No flux is passing through this Gaussian surface. Again, applying Gauss law, you will get phi is equal to Q divided by epsilon naught. As phi is equal to 0, we can conclude Q is equal to 0, which means no charge is inside the Gaussian surface. Now you can imagine that the expansion of that closed Gaussian surface, at any point this is applicable, and you assume that the Gaussian surface expands up to the boundaries of the given conductor. So where are the charges then? The only possibility, the charges cannot reside inside. The only possibility, the whole charge resides over the surface of the conductor. Hence we can prove that the charges can only be distributed over the surface of the conductor, and there is no excess charge inside the conductor. Now come to part B. Another conductor B with a charge small q is inserted into the cavity, keeping B insulated from A. Show that the total charge on the outside surface of A is q plus q. So as an object is placed, object B is placed inside the cavity carrying charge minus q. So naturally then what happened? Here there will be induction of charge. Due to the presence of charge Q inside the cavity, charge minus Q is induced over the surface. And where does the charge minus Q obtain from? Because of the movement of negative charge from the surface, the accumulation of charges is obtained on the inner surface, which means charge minus Q leaves from the outer surface, so that the outer surface is having now an induced charge plus Q. So then already the surface, outer surface has a charge capital Q. Now plus Q is additionally induced, so total charge over the outer surface becomes Q plus Q now. Then let's move to question 29. A hollow charged conductor has a tiny hole cut into its surface. Show that the electric field in the hole is sigma by 2 epsilon naught n cap, where n cap is the unit vector normally outwards. So here we can imagine a conductor with a hole. Like this we can consider a conductor with a hole. Now here the conductor we can call the name conductor A. We are asked to calculate what is the electric field at this point, or we have to prove that electric field at this point is sigma divided by 2 epsilon naught. So for that purpose, we can assume that this whole cavity is filled with the same material as that of conductor. And here we want to calculate the electric field. Okay, and the material field at this point we can take as P. Now the two electric field we can consider now. The two electric field, when you consider, okay, we need to take 2 points, point P and point Q we can take. Now the conductor A is having charge, it produces an electric field E1. A produces electric field E1, and the remaining part, the material field in the hole, can be considered as another object producing electric field E2. Okay, therefore we can first calculate electric field at the point P. Take point P. At point P, the total electric field, we can say the total electric field E is due to two electric fields. What are those two electric fields? We can have electric field produced by the conductor A, can be taken as E1, plus the electric field produced by the material filled in the hole, can be taken as E2. And if the hole is filled, then we can see electric field inside a conductor is 0, which means the values of E1 and E2, okay, the E1 is equal to minus E2. Or if you go for vector concepts, all these quantities are vectors, we can say mode of E1, I mean magnitude of E1 is equal to magnitude of E2. They are equal and opposite. That is why at the point P, those two fields got cancelled. Now, next we can take point Q. Point Q is also having two electric fields, E1 and E2. So total electric field E is equal to E1 plus E2. Total electric field E is equal to E1 plus E2 is equal to, you will get the electric field on the surface of a conductor sigma by epsilon naught n cap, normally outward. In the case of the shell derivation, we have seen electric field on the surface of a conductor is sigma by epsilon naught. Now already we have got E1 is equal to E2. Both are equal. Therefore, we can say 2E1 is equal to sigma divided by epsilon naught n cap. Now we can imagine the original, or we can take the original condition that hole is vacant. If nothing is in this hole, then here electric field is only due to this conductor, only due to conductor. So E1 we can calculate. What is the electric field E1 due to conductor A at the hole? So E1 is equal to sigma divided by 2 epsilon naught n cap. That is a value of electric field produced by the conductor inside the hole. Okay, so that is the proof. Now, next, question 30. Obtain the formula for the electric field due to a long thin wire of uniform linear charge density lambda without using Gauss law. Without using Gauss law. So here we can consider an infinitely long positively charged wire, and we can imagine a point O, and from O we can have an observation point P, a field point P, where we want to calculate electric field at a perpendicular distance r from the conductor. So for that purpose, we can take a small segment dx carrying charge dq, which is so small in such a way that dq can be considered as a point charge. Then we can have dq is equal to lambda dl, linear charge density, lambda dx. dq is equal to lambda dx. dx is the small length of the conductor. Now, here, this dx produces an electric field dE. dE is the electric field produced by the small segment dx at the field point P. And assuming it as a point charge, we can write the equation for dE. dE is equal to equation for electric field due to a point charge 1 by 4 pi epsilon naught dq divided by distance square. Distance square, you have to take this distance, this hypotenuse of this right angle triangle, and square of that distance will be r square plus x square. R square plus x square. Now, here you can see from this diagram, you can at the same time you have to consider a diametrically opposite point. Again, another dx is here, another dx which we can take as dx dash, and that produces an electric field dE dash. dE dash and dE will be equal in magnitude. And those are two electric fields. We can see we can resolve into components. Here you will get dE sine theta, the horizontal component, and here you get dE dash sine theta. Both are equal and opposite. So the sine theta components are mutually cancelled at every point. So what remains there when we consider this dx? So this is the key segment which we are considering, this dx. So electric field produced by dx at point P is not the whole value of dE, but only its component dE cos theta. Sin theta components will be cancelled. Therefore, the electric field due to dx is not dE, but only dE cos theta. Only one component will remain there. Therefore, we can say electric field at the point P, dP is equal to dE cos theta. Only the one component we need to consider there, no need to consider the entire value of d. Now substitute the value of d in that equation. d is equal to 1 by 4 pi epsilon naught. Value of dq we can substitute there. Lambda dx divided by r square plus x square into cos theta. So this is the value of electric field at the point P due to segment dx. Now in this right angle triangle, we can calculate the value of tan theta. Tan theta is equal to opposite side divided by adjacent side, or x is equal to r tan theta. X is equal to r tan theta. Differentiate the equation. Dx is equal to r is constant. Differential of tan theta is 6 square theta d theta. So when you differentiate tan theta, our formula is 6 square theta d theta. Also we can find the value of r square plus x square. R square plus x square is equal to r square plus the value of x is r tan theta, so r square tan square theta is equal to, take r square common, r square into 1 plus tan square theta. Again, for 1 plus tan square theta, we have trigonometric equation, that is 6 square theta. 1 plus tan square theta is 1 plus tan square theta is 6 square theta. Now this value of dx and r square plus x square we can substitute in the equation for dep. This is equal to 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught lambda. In the place of dx we can write r 6 square theta d theta divided by r square 6 square theta into cos theta. Now 6 square theta cancel, 1 r cancel, remaining you will get a dep is equal to 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught lambda divided by r into cos theta d theta. Cos theta d theta. Now you can see in the formula, actually angle theta is the variable now because d theta is. And now we want to calculate electric field due to the infinite length of conductor. Theta is the variable. So what are the possibilities of variation of theta? Suppose the value of x increases. When the value of x increases, theta also increases. Angle theta also increases. So it increases more and more. Finally, up to infinity means you can see this line becomes horizontal. Line horizontal means the angle becomes 90 degree, pi by 2. And this side also you can see here again to the negative side, there also the same way. When it goes to infinity, angle becomes 90. So we can take towards the negative side, it is minus pi by 2. That means theta varies from negative pi by 2 to positive pi by 2. Therefore, the total electric field produced E is equal to, we have to integrate the expression 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught, lambda divided by r, integral minus pi by 2 to plus pi by 2 cos theta d theta is equal to 1 by 4 pi epsilon naught lambda by r. Integral cos theta is sin theta. Sin theta with the limits minus pi by 2 to plus pi by 2 is equal to 1 by 4 pi epsilon naught lambda by r. Then limits we have to apply sin pi by 2 minus sin minus pi by 2. Now again we have the formula sin of minus theta is equal to minus sin theta. Therefore this equation becomes 1 by 4 pi epsilon naught lambda by r, then sin pi by 2 plus this minus sign will come out, so it becomes sin pi by 2 plus sin pi by 2 is equal to 1 by 4 pi epsilon naught lambda by r into sin 90 is 1, 1 plus 1 is equal to 1 by 4 pi epsilon naught 2 lambda by r. It's the same equation we got when we have applied Gauss law also. 1 by 4 pi epsilon naught 2 lambda by r. Then next, it's now believed that protons and neutrons, which constitute nuclei of ordinary matter, are themselves built out of more elementary units called quarks. Protons and neutrons are further divisible into certain subatomic particles which we call quarks. Protons and neutrons consist of 3 quarks each. So there are 3 quarks in protons and neutrons. There are 2 types of quarks. One is up quark denoted by U with the charge 2e by 3, and down quark denoted by D with the charge minus e by 3. Suggest a possible quark composition of a proton and a neutron. Okay. First we take the case of neutron. In neutron, we assume that there are n up quarks. N up quarks. So total number of quarks is 3. Therefore, remaining 3 minus n down quarks. 3 minus n down quarks. Now, construct a charge equation. N up quarks, each up quark having a charge 2e by 3 minus 3 minus n down quarks, 3 minus n minus E by 3. So that is why this equation becomes, the sign becomes negative, equal to total charge of neutron is 0. So you will get, when you simplify, you will get 2e minus, sorry, not 2e, 2n minus 3 minus n is equal to 0, or 3n minus 3 equal to 0, or n is equal to 1. That means neutron consists of one up quark. If one up quark, then 3 minus n down quarks. That means 2 down quarks. Therefore, neutron can be represented. A neutron you can write in terms of quarks as U, one up quarks denoted by U, 2 down quarks, so UDT. Next, take the case of proton. The same way we can write the equation, same assumptions we can take. There are n up quarks, and 3 minus n down quarks. So make the charge equation. We have n into 2e by 3 minus 3 minus n into e by 3 is equal to charge of proton is E. Simplify the equation in the same way. You will get the answer n is equal to 2, which means proton consists of 2 up quarks and naturally 1 down quarks. So you can represent proton as UUD, 2 up quarks and 1 down quark. Now, next, question 32. Consider an arbitrary electrostatic field configuration. A small test charge is placed at the null point. Null point means E is equal to 0, which means there is no electric field. E is equal to 0 of the configuration. Show that the equilibrium of the test charge is necessarily unstable. So here we take an arbitrary point, and the speciality of this point is mentioned in the question. Electric field is 0. No electric field. Now assume a Gaussian surface around this point. When you assume the Gaussian surface around this point, you can see, being electric field 0, no flux is entering or emerging through the surface. As no flux is entering or emerging through the surface, then what will happen? Suppose I place a test charge Q here. When the test charge Q is placed, then this test charge will not experience any force. If electric field is present, then you can see the test charge will experience a force either in the direction of electric field or opposite to the direction of electric field. Depends on the nature of the charge, electric field, etc. Anyway, a force will be there. Now, but we know there is no electric field. No electric field means no force. No force on test charge. No force. Now just assume that, okay, the test charge is placed so-called null point. When you place the test charge at the null point, F is equal to 0, no force. So we can say the test charge is at equilibrium. Okay, at the null point, the test charge is at equilibrium. Now, suppose I displace the test charge from that point. The test charge is now displaced to another point. It will remain there. What is the reason? Because no electric field here, no flux is passing through the surface. And if I displace the test charge to another point, there is no possibility for the test charge to come back to its original point, say the point O. So at 2O charge is at equilibrium, but if I displace the charge from the point O, the charge is not going to come back to the point O. So far the electric field is not there. If electric field is present, there is a possibility because of the force applied by the electric field, it can come back. But now no such possibilities. Therefore, if at the null point the test charge is at equilibrium, but if it is displaced from the null point, it cannot come back to the same point. Therefore, as it cannot come back once displaced, the equilibrium is unstable equilibrium because it cannot come back. Now, take part to B. Verify this result for a simple configuration of two charges of same magnitude and sign placed a certain distance apart. So for case B, we can take two charges Q of same magnitude and a test charge is placed at the midpoint O. Test charge Q is placed. Now you can see over the test charge, both the charges will apply a repulsive force so that the net force at this point is 0. So net point is 0. So we can say charge small q is at equilibrium at the point O. Now, if I move the test charge towards left, what will happen? When I move the charge towards left, the force between the charge in the left side and small q will increase. The repulsion will increase so that the test charge will return back to the point O. If I displace the test charge close to the charge at the right hand side, then again you can see along the straight line. If it is moved along the straight line, then it moves towards here. The repulsive force between the charge at the right end and the test charge will increase so that the test charge will come back to the equilibrium position. Therefore, we can say along the straight line joining the two charges. I repeat, along the straight line joining the two charges, the test charge Q is at equilibrium, and that equilibrium is a condition of stable equilibrium. What is the reason it is a stable equilibrium? Because whenever the test charge is displaced along this line, the test charge will, the repulsion increases and the test charge will return back to its original position O. Therefore, the point O, the test charge is at a stable equilibrium. The force is 0 and it will come back to the same point. So the equilibrium is a stable equilibrium. But at the same time, you consider an equatorial plane here. Now, if I move the test charge to a point here, another point, say O dash, what will happen? Both the charges will repel the test charge like this. Repulsion will be there. The resultant repulsion is acting along the midpoint. So the charge small q will continue to travel in this direction because of repulsion. It is not going to come back to the point. So if I displace the test charge small q from the point O along the perpendicular bisector, then the test charge q is not going to come back. Therefore, along the perpendicular bisector, if you consider this equilibrium is unstable equilibrium. What is the reason? It is unstable equilibrium. When the charge moves along the bisector, it is not going to come back. So, finally we can conclude, along the line joining two charges, capital Q's, the test charge small q is at stable equilibrium. But along the perpendicular bisector, it is at unstable equilibrium. Okay. Now, question 33. A particle of mass m and charge minus q enters a region between the two charged planes, initially moving along x-axis with speed vx. The length of the plate is L and uniform electric field E is maintained between the plates, so that the vertical deflection of the particle at the far edge of the plate is QEL square by 2m Vx square. So this is a continuation of question 14. In question 14, we have derived the equation for vertical deflection. Y is equal to vertical deflection y is equal to q e by 2m into t square, and the acceleration qe by m is acting along y axis. If you have two horizontal plates like this, L is the edge length of the plate. Now the force is acting along y axis, no force is acting along x axis. The reason? The electric field applies force along y axis only. Electric field, this is positive plate and negative plate. Electric field is from positive plate to negative plate. So force is only acting along y axis, no force is acting along x axis. Therefore, along x axis, the velocity of the body will be a constant, and that velocity is given as Vx. So we can say Vx is equal to distance, that is length L divided by time, or time t is equal to L divided by Vx. So substitute this value of L in the equation. Vertical deflection y is equal to QE divided by 2m into L square divided by Vx square. So that is the proof. Now, next question 34. Suppose the particle in the previous question is an electron projected with velocity Vx is given, electric field is given, and where will the electron strike the upper plate? So the same diagram we can take like this: two plates, positive plate and negative plate, edge length L. So here, when you project the electron, we assume that the electron is projected through the midpoint. Once it enters in the field, electric field acting from positive plate to negative plate, now this electron will bend and it will strike at a point here, and that distance is taken as L. And so what is the value of y deflection? This is the value of y deflection along y-axis when it strikes the plate. So you can take now y is equal to 0.5 centimeter divided by 2, assuming the particle is projected along the center line of these two plates. So you will get the value of y as 0.25 centimeter. Now you are asked to calculate where will be the electron strike the upper plate. That means L you have to calculate. So use the formula in the previous question. Y is equal to QE L square divided by 2m Vx square. Value of y is 0.25 centimeter. Cross multiply the equation and find the value of L. So this is the exercise questions of the chapter.